Welcome back to our video module on dynamics. We've spent quite a bit of time recently looking carefully at polar vectors and trying to understand them at a more intuitive level. Today, I'd like to revisit what we know about momentum, energy, and changes in those characteristics to more fully understand how to apply polar vectors to these ideas. We'll be using just circular motion to develop these insights today. I should note clarifications I need to make. The first is in yellow, the polar velocity. It seems I've scrubbed out the plus, so it looks like a minus. In fact, that should read r dot er plus r theta dot e theta. My apologies for any confusion. Secondly, in the rectangular coordinate frames, we'll be looking at x dots, y dots, and in fact, if I wanted to make a true parallel between rectangular coordinate frames and polar coordinate frames, we'd be looking at our angle and our radius. So we define our x's and our y's in terms of r's and thetas. But I hope this more simple approach preserves the clarity of the comparison. So first, I'd like to start us off with linear momentum. We know linear momentum is defined by mass times velocity, and it's a vector quantity. So in rectangular coordinates, it's simply m times x dot I plus y dot j. This should be review for us. In polar coordinates, let's look at our circular motion. We know that the radius is staying the same. So the only velocity that we're going to worry about is going to be this component of the velocity. So we simply take mass times r theta dot e theta. Let's help out that hat right there. So our linear momentum is just looking at the tangential velocity combined with the mass. Next, we'll take a look at the change in linear momentum. This is mass times acceleration, and in rectangular coordinates, it's once again pretty simple. mx double dot I plus y double dot j. And in polar coordinates, we're now we're looking at circular motion, so we're keeping our radius constant. And we know that the overall acceleration is going to be r theta double dot in the e theta direction minus r theta dot squared in the er direction. We got that by simply looking at the acceleration in polar coordinates. Does this make sense? Well, a change in linear momentum in the tangential direction, if we have a change in that velocity, which would be right here, that would be a change in the linear momentum. That would basically be a change in that direction. And in addition, the linear momentum is facing this direction 1 second, and then the next second it's facing this direction. It's really going to be a function of whatever is happening in the ER direction. Next, let's take a look at angular momentum. Remember that angular momentum about, say, some point, in this case, let's do the center, point O, is going to be the position with respect to point O crossed with a mass times the velocity. And if you wanted to do that in rectangular coordinate, you'll end up with x y dot minus x dot y in the k direction, and something that makes a little bit more sense in the polar coordinates, you'll have m times r squared theta dot in the k direction. We got that by taking the position. We know the position is only in the ER direction crossed with the velocity. Well, and something in the ER direction crossed with the ER is going to be 0. So we have an ER crossed with an E theta. We know that goes in the K direction. We end up with an R times a theta dot, R squared theta dot. And of course, there's an M in there. The next quantity we want to take a look at is another vector quantity, and that's the change in angular momentum with respect to O. This is simply the distance or position with respect to O crossed with mass times acceleration. And in rectangular coordinates, you're going to end up with something fairly simple, except now we're looking at second derivatives instead of first in the k direction. And in a polar coordinate frame, we'll have m r squared theta double dot. Okay, you have two ways of looking at this. One is we're going to look at the change with respect to time of this. Well, this value r is not changing, m's not changing, so it must be theta double dot. Another way to find it is by using the same reasoning we used before, where we look at the position with respect to O. That's going to be in the ER direction. So if we're finding a cross product, this whole term right here, that's all going to disappear. We know that our Coriolis term is going to be 0 because we're not changing the radius, and we're left with r times theta double dot. Next, let's take a look at energy. Now, energy is not a vector equation, or a vector value, but we do know that it's 1/2 mv squared. In rectangular coordinates, that's going to be 1/2 mass times the magnitude of the velocity squared, which is simply x dot squared plus y dot squared. And in polar coordinates, we're going to have 1/2 mass times r squared theta dot squared. Might be wondering, where do we get that? Well, let's look at our velocity. Our velocity, we have nothing going on in the radial direction, so we must take this term, that is its magnitude, so we just square each of the terms, and we end up with r squared theta dot squared. Finally, let's take a look at the change in kinetic energy. The change in kinetic energy is also known as the power. We can find that as F dot V, but we want to reduce this into terms like position, velocity, and acceleration. And if we do that, we find that mass times velocity dot A is our change in kinetic energy. And in rectangular coordinates, that's going to be fairly simple. That's going to simply be mass times x dot x double dot. Remember, we're taking the dot product, so that'll be y dot y double dot. This will be a scalar. And in polar coordinates, our final result is mass times r squared theta dot theta double dot. Where do we get that? We're going to use the same process we've been using. We take our velocity dotted with our acceleration. Now we know that nothing's happening in the ER direction, so we know we'll only look at the E theta direction. This is going to go to 0, so we're looking at this term right here and this term right here dotted together, r squared theta dot theta double dot. Hopefully this tabular form gives you a good feel for how we can use our polar vectors, their velocity and the acceleration, as well as giving you a little deeper understanding of momentum, energy, and how they change with time, especially with circular motion. Thank you, and I look forward to seeing you in our next video module.